I'm already getting sick, so I'll just pull through until Tuesday.
Yeah, put it in.
Like I really have work, and then like every day after work, I have like a Christmas event. And I'm gonna like film the Christmas event. Like I'm planning. I can't read it.
Yeah, like that can never be.
Mom was like, yeah, I'll just come back with that. She was like, like, it's just not happening. But like, no. I really don't. And then usually like this is the one that she fails. It was like great.
When I'm sorry.
I was like great. But I'm not. I can do it.
Review all secondary. Yes.
Like try. This is like there's nothing you
I
can
say
say.
it every Wednesday.
I remember. At least somebody's no hope, and I was like, no, like I'm not gonna do that. Yeah,
I wish you cried after school. I feel very old.
well, the first one I failed, I was like, what am I doing with my life? And then I was like, oh, man, I would be really throw like a party.
Like you want 70.
You're 70. Like the tallest good job, and like the median is like 65. And I'm like, yeah,
Hey. Yeah.
I know.
But he can, or just.
I got that second.
So I think it's Tuesday. I got that second call first.
Yeah, I mean, if you can't find it, I'll still give you. If you want to take it, please.
Could I, I'm not gonna do this. Early. Sorry.
We'll be here.
Yeah.
I don't know.
It's just for today.
Second part.
Pretty
See, I
sure.
wrote,
Mine is kind of like.
Okay, let me go over what we're gonna do between today, tomorrow, and Monday. So there's one more grade remaining, and that's gonna be a quiz grade. Most of it is gonna be on Monday. The rest of it is just finishing up this multiple choice kind of a cumulative review of things that we've covered this semester. But this is just a completion grade, and I think we can do most of this in class, if not all of it in class. So there's 6 pages to this. I think we can do 2 pages a day, if not more than that. Then whatever we can't finish today and tomorrow, we can finish it on Monday. So, and then each day at the end of class, I'll just walk around and see that you've completed up to the point that we've done in class. And so just by completing it in class, that's 50 points quiz grade. And then the other 50 points for your quiz grade is going to come from the quiz, just going through, filling out this rules and theorems and derivative sheets on Monday. And it'll look just like this. I'm not going to make any changes to it. The order, everything is just like it. So, yeah, so, most if not all, we should all get, 100 or at least close to 100 with this quiz grade on Monday. Any questions? And I hope to have, I know once you take it on Monday, I hope to have it all graded Monday night, put in the grade book. So if you realize that you made some mistakes and you want to come back and retake this derivative quiz, then you can come in Tuesday through Friday, any of those days to come in and retake it and try to get a higher grade. Okay. So let me just start off by going over the rule sheet. And so you guys can start looking at it and start practicing through it over the course of these next few days leading up to Monday. So, if you were to take it right now, you'll probably get most of this first page just from what you've worked on, leading up to this previous test. So first off, we have power rule. This is a rule that we've been working on through this whole semester. And then the trig derivatives, you guys were responsible for knowing that for the test. And then e to the u and natural log of u, you guys also should be pretty familiar with that. And then the arc trig derivative rules. We just recently learned that. And so really the only thing that you may be a little unfamiliar with is just the log base a rule and the a to the u rule. Okay. But again, just to kind of highlight the connection with these rules is with the ones above it. Natural log is u prime over u. Log base a of u is still a log derivative. So still u prime over u, but with a little bit of conversion that has to happen. So there's a 1 over natural log of a that's coefficient u prime. E to the u and a to the u are very much related. They're both exponential functions. E to the u is the original function times the exponent's derivative. A to the u is also the original function times the exponent's derivative. But it's not base e, so there's a conversion that has happened for natural log of a. For log base a, the natural log of a is in the denominator. For the exponential, the natural log of a is in the numerator. So what helps remind me is I look at the rest of the rule. I don't see any denominator, so that helps remind me natural log of a is in the numerator. Here, u prime over u, there is something in the denominator, so that helps remind me the natural log of a is in the denominator for the log base a rule. And so really, you're just having to add 2 new rules that you weren't responsible for from the previous test. Okay, back page. All right, most of these theorems you should know already. IVT, if a function is continuous on the closed interval from a to b, then there exists a c value where f of c lands between f of a and f of b. So all it's saying is if I have a target y value that I'm after, then I need my endpoints, 1 to be above and 1 to be below my target. And then I can guarantee my graph is going to be is going to reach that target. Now, every theorem has a continuity condition to it, but we only include differentiable conditions for mean value theorem and Rolle's theorem. These are the only ones that have a slope component to it, so that's why we need that differential. But we don't need a differentiable for IVT and extreme value. So if you indicate differentiable with IVT or extreme value theorem, that's incorrect. Okay, we don't need that condition. So IVT and EVT have all four have continuity, but only mean value theorem and Rolle's theorem have the additional differentiable condition. Extreme value theorem, we test endpoints and critical points to find the absolute max and absolute min. Mean value theorem, if f of x is continuous on the closed interval and differentiable on the open, then there is at least one point where the instantaneous rate of change is equal to the average rate of change. So basically, this formula, we just have to be able to verbalize what it means. Slope is the average rate of change. Derivative is the instantaneous rate of change. Rolle's theorem is pretty much identical to mean value theorem. It's just that this piece has to be zero. In order for that piece to be zero, we just have to show that f of a equals f of b. Okay. Product rule, quotient rule, chain rule. You should be fairly familiar with those. L'Hopital's rule says if my limit, if I do direct substitution with my limit and I get 0 over 0 or infinity over infinity, then I can repeat the same process with the limit after I find the derivative of the numerator and denominator separately. And then log properties, product property, I can expand a product within a log into the sum of two logs. Quotient property, I can take quotient within a log property and expand it into the difference of two logs. And power property, within the log expression, I can bring that exponent down in front. So I gave you a blank copy, and then I also attached a key so that you guys can begin looking at it and practicing in preparation for Monday. Any questions with the derivative and rules quiz for Monday? Okay, all right, let's see if we can make progress with the cumulative review. Right, let me start off by number one. It says use continuity conditions. So let's review continuity conditions, and then we can just step through it. So there are three conditions. And they are these. Okay. The first condition is, does the point exist? F of c. Let me zoom in a bit here. Second condition is, does the limit exist? Sometimes it's just evaluating a limit, but if you have a piecewise function with less than, greater than, then we may have to go a little further and actually evaluate the limits of both the piecewise functions and to see if they are headed towards the same y value. And then if the limit exists, then we can go to the third condition. Third condition, we don't find any new data. We're just comparing what we've gathered from 1 and 2. So whatever we get from 1, whatever that point is, and then wherever the limit is, we compare to see if they are in agreement. If they are in agreement, that means whatever hole was created here is getting filled in by the point. So if it passes the second condition, sorry, first off, if it fails the second condition, that means we have disconnected graph. If we have disconnected graph, that means it's a non-removable discontinuity. But if it passes the second condition but fails the third one, that means that there's a hole that it's not getting filled in. And if it's not getting filled in, then there's a removable discontinuity. And then obviously, if all three conditions pass, then we have a continuous function through that point. Okay, so all right, first condition. Does a point exist? Well, you're always going to be told what point to consider. So in this case, 0 is our focus here. And 0 is defined with the second piecewise. So we can say f of 0 is just 0 squared plus 1, which is 1. So it passes the first condition, no issues. Second condition, does a limit exist? Well, we have two different graphs on either side of 0. So we need to look at the limit from both sides and see if they're actually in agreement. So we have to do one-sided limit. So we'll look at the limit as we approach 0 from the left side of 0 for cosine of x. And then separately, we'll find the limit as x approaches 0 from the right side of 0. And from the right side of 0, we're looking at the x squared plus 1. Now, with one-sided limit, we basically ignore that notation. We just plug in that integer value. See what we get. So cosine of 0 is 1. 0 squared plus 1 is also 1. So my one-side limits are in agreement. Therefore, we can conclude that the full limit of f of x must also equal to 1. So limit exists, but we keep going. In the third condition, we're just comparing what we came across that we've accumulated so far. And obviously, the order pair and the limit are the same. So we can say f of 0 is equal to the limit as x approaches 0 of f of x. And therefore, all three conditions pass. We must be looking at a continuous function. Okay, by continuity conditions, f of x is continuous at x equals 0. Okay, and I've got the key attached to the back of your handout. Number 2, says the function f is continuous at x equals 1, solve for k. We're basically just going to do the same thing here. We're just going to step through our continuity conditions. And then by the time we step through all three conditions, we should be able to have k show up with a value that we're looking for. But if you look, this piecewise looks a little bit different here. This is less than greater than. This one is doesn't equal to. So the difference is that these are two separate graphs, right? But this one is a graph and a point. So when you see doesn't equal to 1, that means it's everywhere except 1. So to the left of 1, it's this graph. To the right of 1 is this graph. But this is just a single point. So when we're dealing with limits, we're dealing with the graph and not the point. So if you see this notation, we only do limits with the connected parts of graph. We never do a limit with the point. But here we have two separate connected parts of graph, so that's why we needed to do a limit both times, once coming from the left side of 0 and the other coming from the right side of 0. All right, so here's number 2. So we know that the x value in question is 1. So let's find f of 1 first. F of 1 is equal to k, which is the unknown. So we keep going, can't do anything with that. Second condition, does a limit exist? We talked about how this notation tells us that the graph is all contained within this piecewise. We don't look at limits with a single point. We'll look at the limit with the graph. So we should need to write one limit statement. All right, first thing we do with limit is we always do direct substitution. So if we plug in 1, we get √4 minus √4, which is 0. We get 0 over 0. On my key, I went through the conjugate method, but we could also try L'Hopital's rule. With L'Hopital's rule, though, we do have to go through a chain rule twice. So, but yeah, we can try that. Yeah, let me rewrite this. Okay, so derivative using chain rule, we get 1/2 x plus 3 to the negative 1/2 times 1, because that's the inside derivative, minus 1/2 outside derivative, 3. All over, x becomes 1 and 1 goes to 0. All right, let's plug 1 in and see what we get. 1 plus 3 is 4, so it's 4 to the negative 1/2 minus 1/2. 3 plus 1 is 4. 4 to the negative 1/2 times 3. Denominator is just a 1 here. If I clean this up, I'm really putting a 4 in the denominator, and I'm taking the square root. So it's 1/2 times 1/2. Right, square root of 4 is 2, and I got to put that in the denominator. Now here, I have 3/2, and then square root of 4 in the denominator is also 1/2. So I have 1/4 minus 3/4, which is negative 2/4, which is negative 1/2. So the limit is equal to negative 1/2. So that fulfills the second condition. Now the third condition, we need the first two to agree if we want continuity. So f of 1 equals k, limit is negative 1/2. In order for these two to agree, I have no choice but to make k equal to negative 1/2. So we're using continuity conditions to help pave the way for us to get to the variable that we're looking for. Okay, number 3. All right, given h of x equals g of f of x, find h prime of 2. Now, before we can find h prime of 2, we first have to find h prime of x. To find h prime of x, this is a function within a function. We got to go through chain rule. So let's build out the derivative using chain rule. Outside derivative times inside derivative. Right? Replace every x with 2. Let's do one piece at a time. We're not going to be able to get to our answer in one step. So multiple steps here. This is complicated, but let's do the piece that feels manageable, right? We can find f of 2. That's just finding the y value of the f graph at 2. So let me highlight the f graph here. So f of 2 is here. That's just the y value, right? So f of 2 is equal to 3. So I'm going to rewrite my entire expression, but I'm just making one replacement. Just doing one thing at a time here. Okay, so now this feels a lot more manageable because the only thing left to do is we need to find f prime of 2 and g prime of 3. We know derivative is basically slope, so we want to find the slope of the f graph at 2, and then separately we'll find the slope of the g graph at 3, and then we'll get those numbers and multiply them together, and that's our answer. So f prime of 2, that's a nice straight line here. We just have to figure out the slope of this graph at this point. Now this, if I follow this line here, down 1/1, this is a slope of -1 here. So I know that f prime of 2 is -1. And I also need to find g prime of 3. So g prime of 3, g graph is on the other graph here. Now this doesn't land at a point, but it's okay. We're like asking for the slope, not asking for the order pair. So I just have to figure out from end to end along the segment, what is the slope? And I can go up 2/3, right? So the slope of this line segment up 2/3, 2/3. So g prime of 3 is 2/3, f prime of 2 is -1. We just pair those together. Okay, number 4, find h prime of 1. This should feel pretty familiar. I think quotient rule can get us to this, right? So we can't just say k prime over 3, though, right? We have to go through a full quotient rule. So, yeah, try that. F prime g minus fg prime all over g squared. Once you build out your derivative using quotient rule, then replace every x with 1, and then use the table to make your final substitution to get it down to a number. Okay, check your answer here. F prime g minus f g prime, k becomes k prime, 3x stays, k of x stays, and 3x becomes 3, all over denominator squared. So make sure we square both the 3 and the x. And then once we have our derivative, replace every x with 1, and then we go to our table. Okay, next up, number 5. We should be familiar with this. We just took a test on it where if you see a trig function, take the time to rewrite it, right? If you don't put that exponent outside, it's harder to see the whole chain rule process that we need to go through. Okay, so try number 5. Outside is your bracket square, inside is your tangent. You're just going through, right? Bracket square becomes 2 brackets to the first power. Tangent of u becomes secant squared u times u prime. Then we can push all the coefficients, the non-trig terms in front. Okay, any questions with 5? All right, number 6 is relating a function and its inverse. And let me just, we'll go through that chart. So let me kind of talk about that chart that we build in terms of expanding or in terms of connecting the relationships here. So we have a function and its inverse, right? And the inverse, let me call it f inverse, always will have an order pair that's flip-flopped with the order pair on the function side. So if there's an order pair 5, 3 that lives on the inverse, then there must be an order pair 3, 5 that lives on the function. Okay. And we're always going to start off this way where we're trying to find the derivative of f inverse at some value. But everything that we're going to be given is going to be on the function side. So we just have to know that, okay, whatever number they give us is going to be the y value on the function side. And then we just have to go through and work backwards to figure out what is the order pair on the function side. And then once we find that value, then we can find the slope of the function at that point. So we find the derivative, find the slope, and then whatever slope we find, it could be 2/5 or 1/3 or 4/5 or 6. We're going to take that number and we just do the reciprocal. Once we find that reciprocal, we have our answer. So we're always starting down here in the bottom corner, and we're working our way around the chart. And by the time we make our way around the chart, we have enough information to come back to conclude our answer. Okay, so here's our process for number 6. We're always going to start at the bottom corner. Bottom corner is our target. We're trying to find the derivative of p inverse at 5. Now, we know that 5 is the x value of the inverse function. But if 5 is the x value of my inverse, then 5 must be the what of my original? Must be the so if 5 is the x value of the inverse, therefore 5 is the what of the original? The y value, yeah. So whatever number they give you is always the y value of the one that you're working on. So you know that p of some x value is equal to 5. So understand that you're just going to have to work backwards. The 5 is going to go in your y position, and you're going to work backwards to figure out what the x is. Right. So 5 is equal to cube root of 2x minus 1. Sometimes it's guess and check, but I think in this case, we can work it out. So there's only one variable x, so this one we can work by hand. So let's cube both sides. Five cubed is 125. Cube root of something cubed is just the expression inside. So I'm going to add 1 and divide by 2. So now that I have my x value, I'm going to fill this in here, 63. Okay, I should be able to establish that relationship here. There's an order pair 63, 5 on the function, which must mean there's an order pair 5, 63 on the inverse. So if I can find p prime of 63, then whatever number I get will lead me to my answer. So before I can find p prime of 63, let's first find p prime of x. To find p prime of x, we'll just go through chain rule. outside's derivative, parentheses to the 1/3 becomes 1/3 parentheses to the negative 2/3. And then after we're done with the outside portion, we move on to the inside. 2x minus 1 becomes 2. Now we can, if you want, you can clean it up a little bit, but we're going to eventually plug in that 63. It feels like you have to do this in your calculator, which you can, but we can also do this without a calculator. It seems like it's hard to do trying to square 125, but if you focus on doing cube root of 125, that feels a lot more manageable, right? Cube root of 125 is just what? 5, yeah. And then once we have 5, it's easy, right? 5 squared is 25. Sorry. 2 over 75. So if my slope is 2 over 75, then if I flip that, then the derivative of f inverse will must be 75 over 2. Okay, number 7. Y squared minus 3x equals 7. Find d2y over dx2. So we know there's implicit involved, but we have to do it. We have to find the second derivative here. But let's find dy dx first. Okay. Y squared becomes 2y dy dx. 3x becomes 3. And then 7 goes to 0. Let's solve for dy dx first, and then we can move into d2y over dx2. Okay, divide both sides by 2y. So I'm halfway there. If I want to find the derivative again, I could go through quotient rule, but typically we can avoid quotient rule if one of your sides is missing a variable. I can just bring this y up and think of it as 3/2 y to the negative 1 and just rely on power rule. But another implicit here, because we have y for us to find the derivative. So d2y over dx2, that's our second derivative. 3/2 stays. Power rule for y to the negative 1 is negative 1 y to the negative 2. And we're asking for y's derivative, so we need to attach dy dx. Typically, if you see this type of problem, it'll be like in the multiple choice section. And if it's multiple choice section, what they're going to do is they're going to try to represent their answer all in terms of x and y. So our final thing to do is to replace the dy dx back with the dy dx that we found from before. So we have our second derivative, but we can represent our derivative with those replaced, with that dy dx replaced. So I'm going to do some cleanup here. I'm bringing that y squared back down to the denominator, share the same space, that's the 2, and then replace dy dx with 3 over 2y. And this is a little bit cleaner. Therefore, negative 9 over 4y cubed. Okay, if I can just come around real quick, you can just show me the first 2 pages.
Oh, yeah.